You've watched this from the gate 100 times. A squat, low-slung vehicle drives up to the nose of your airplane, hooks on, and casually pushes 500 tons of metal, fuel, and passengers backward across the tarmac. Most people figure that tractor must have a monstrous engine inside it. Something industrial, something measured in thousands of horsepower. It doesn't. A standard wide-body pushback tug runs on roughly 500 horsepower, about the same as a heavy-duty pickup truck. So how does a pickup truck engine move a fully loaded airliner? The answer has almost nothing to do with power. It involves a piece of metal designed to snap in half, 70 tons of dead weight that exist for no other reason, and a trick that turns the airplane's own mass against it. The intuition tracks with everything you know from daily life. Pushing a stalled car to the shoulder takes 2 or 3 people straining against the bumper. Moving a loaded shipping container across a floor requires a forklift. So a 575-ton Airbus A380, the combined weight of roughly 400 compact cars, should demand something approaching locomotive-grade force. And here's what makes the assumption even more reasonable. The airplane doesn't strictly need the tug at all. Pilots used to move jets backward under their own power, deploying thrust reversers at the gate and redirecting jet exhaust forward. The procedure was called a powerback. It worked. It also turned the gate area into a windstorm that flipped 5-ton baggage carts, cracked terminal windows, and blasted ground crews with debris at highway speeds. Airlines abandoned the practice at virtually every major airport, not because it failed, but because it succeeded too violently. So the pushback tug became the only safe way to move a jet away from a terminal. But the engine inside it is modest, comparable to a heavy commercial truck. The way it actually moves the airplane starts with a number that seems too low to be real. Aircraft tires are inflated to between 200 and 320 psi, roughly 6 to 10 times the pressure inside your car tires. That extreme pressure makes the tire almost perfectly rigid. Where it contacts the pavement, it barely deforms at all. And that tiny, hard contact patch, rolling across a smooth concrete apron, means the rolling resistance of an airplane is remarkably low. The coefficient is about 0.015. In practical terms, to keep a 575-ton A380 rolling at a steady walking pace, the tug needs to exert roughly 19,000 pounds of horizontal force. 19,000 pounds sounds enormous in isolation. It isn't, not at this scale. That's less force than it takes to pull a loaded semi-truck up a moderate highway grade. A single industrial diesel engine can generate it, but the trick is in the transmission. The gearing sacrifices speed for torque, spinning the engine at thousands of revolutions per minute to turn the drive wheels a few degrees at a time. That diesel rumble you hear through the cabin during pushback, the engine revving high while the plane barely creeps backward, that's not the sound of a machine overwhelmed by the load. It's the sound of gear reduction converting rotational speed into a slow, crushing twist at the axle. The airplane, for all its mass, rolls easily. Moving it is the easy part. The hard part is getting that force from the engine to the ground. The tug's drive wheels have to push against the concrete to move the airplane, and for the wheels to push without slipping, they need grip. Grip depends entirely on weight. How hard the tires are pressed into the surface determines how much horizontal force they can deliver before they break loose and spin. If a lightweight tug tries to push a 575-ton airplane, the result is predictable and absolute. The drive wheels spin uselessly against the pavement, like a car stuck on ice. Torque without traction is just noise. So, conventional pushback tractors solve this the most direct way possible. They carry ballast, thick steel plates, and dense lead slabs, dead weight that serves no mechanical purpose except pressing the tug's tires harder into the tarmac. A conventional wide-body tug can weigh over 70 tons, heavier than an M1 Abrams battle tank, and nearly all of that mass is parasitic. It exists solely to prevent wheel slip during 5 minutes of pushing. 70 tons of dead steel, hauled across an airport all day for 5 minutes of useful traction. It works, but it creates a problem far more dangerous than wheel slip, because that entire 70 tons is now connected to the most structurally fragile part of the airplane. That metallic clunk you hear through the floorboards right before the push, that's a rigid steel towbar locking onto the aircraft's nose landing gear. The nose gear is engineered to absorb enormous vertical impacts during landing. It is not engineered to withstand enormous horizontal forces from a 70-ton machine pushing, braking, and steering against it. If that sounds like the setup for ripping the front wheels off a $300 million airplane, it is. The towbar contains a shear pin, a precision-machined steel cylinder, roughly the size of your thumb, explicitly designed to be the weakest link in the chain. Its metallurgy is calculated to hold firm under normal operating loads, but fracture violently the instant the force exceeds the aircraft manufacturer's structural limit. For a Boeing 737 MAX, that limit is 29,000 pounds. 1 pound beyond it, and the pin snaps, the towbar separates, and the tug is physically disconnected from the airplane before the stress can reach the airframe. These aren't standard bolts from a hardware store. They're manufactured in controlled batches, stamped with serial numbers, and destructively tested. Samples from every production run are loaded in a lab until they snap, confirming they fail at exactly the specified force. Too weak, and the pin breaks during routine pushbacks, grounding departures for no reason. Too strong, and it transfers the tug's full torque into the nose gear, defeating the entire purpose of having a fuse. The connection between a 30-ton tractor and a 500-ton airplane is engineered around the certainty that it will break. And before any of this can happen, someone has to walk up to the nose gear and insert a small metal pin into the steering assembly. This bypass pin releases the aircraft's hydraulic nosewheel steering, which operates at 3,000 psi, roughly the pressure a mile deep in the ocean. Without it, the nosewheels are hydraulically locked in place. The tug could push straight back, but the moment it tried to turn, it would be fighting that 3,000 psi system, enough force to snap the shear pins before the airplane moves an inch. The bypass pin lets the wheels swing freely, giving the tug full steering authority without triggering the very fuse designed to protect the airframe. Everything so far, the ballast, the shear pin, the bypass pin, describes how pushback worked for decades. It's effective. It's also enormously wasteful, burning diesel to drag 70 tons of dead steel across an airport, maintaining stockpiles of different towbars for every aircraft type, trusting a single sacrificial pin to protect a multi-hundred-million-dollar airframe. Engineers found a way to eliminate all of it, and the physics behind it are almost embarrassingly simple. If you want the next one of these to show up in your feed, subscribing takes 1 second. Modern towbarless tractors carry no ballast and use no towbar. The tug drives up to the nose gear, extends a hydraulic cradle around the tires, clamps them, and lifts the entire nose assembly slightly off the ground. The nose gear of a commercial aircraft supports roughly 10 to 15% of the airplane's total weight. On a fully loaded A380, that's about 57 tons. When the towbarless tug lifts those wheels, all 57 tons transfer directly onto the tug's own drive axle. A tug weighing 25 tons instantly behaves like an 82-ton vehicle, with all the traction that implies without carrying a single slab of dead ballast. The airplane's weight was the obstacle. Now it's the tool. When the pushback is complete and the tug lowers the nose gear, it sheds that borrowed weight and drives away as a lightweight vehicle. A single towbarless tug works with virtually any aircraft type. No swapping towbars, no storage yards full of specialized equipment. And because the connection is rigid rather than articulated through a flexible bar, these tugs can reposition aircraft at up to 20 miles per hour, double the safe limit of the old towbar systems. The latest generation is fully electric, with the heavy battery packs doubling as traction weight. The dead ballast problem solved by a component that actually earns its mass. Without a physical towbar, there's no shear pin to protect the nose gear. Modern towbarless tugs replace it with electronic load cells, force sensors in the cradle that continuously measure the torque on the landing gear. If the steering angle or braking force approaches the aircraft's structural limit, the tug's computer cuts engine power and bleeds hydraulic pressure in milliseconds, arresting the maneuver before the metal begins to fatigue. What happens when those limits are exceeded was demonstrated at Newark in 2006. A Boeing 737 was being towed when the forces on its nose gear passed the structural threshold. The upper and lower drag braces fractured. The lock brace failed. The entire nose gear collapsed forward, dropping the front of the airplane onto the concrete. One incident, millions of dollars. Every structural tolerance governing every pushback, whether enforced by a breakable pin or a software algorithm, exists because the consequences of exceeding them are not gradual. They are instantaneous. And at gates that still use conventional towbar pushbacks, which is most of them, there's a moment worth watching for. After the push is complete, before the airplane taxis, a ground worker steps into view beneath the cockpit and holds a bright red ribbon overhead. Printed on it, "Remove before flight." That ribbon is attached to the bypass pin, the one inserted before the push to release the hydraulic steering. The pilots cannot taxi the airplane until they see that pin confirmed removed and the steering returned to their control. The red flag isn't a wave goodbye. It's the final mechanical handoff between the ground and the cockpit. All of this physics depends on one condition engineers can't control: the surface under the tires. On dry concrete, the coefficient of static friction between rubber and pavement is about 0.8, excellent grip. On ice, it collapses to 0.1. When that happens, the math stops working. A 70-ton conventional tug that grips the surface effortlessly on a July afternoon can barely generate enough traction to overcome an A380's rolling resistance on a frozen January morning. The drive wheels spin. The airplane sits. Airport operators fight this with brute pragmatism. Steel chains on the drive wheels, abrasive sand scattered across the apron by hand, and a technique that sounds wrong but works. Ground crews deflate the tug's tires from 60 psi down to 25, letting the rubber flatten and spread across a wider contact patch that bites into the ice instead of gliding over it. Towbarless tugs handle winter better for the same reason they handle everything better. The 50-plus tons of aircraft weight pressing down through the cradle crushes the tug's tires through the ice layer and into the pavement beneath, restoring traction that no amount of dead ballast can match on a contaminated surface. Next time you're at the gate, pay attention during pushback. The slight shudder through the cabin, that's the tug breaking the airplane's static grip on the pavement. The moment rolling resistance transitions from breakaway friction to almost nothing. And at the end, the ground worker holding up a red ribbon for the captain to see. A small pin pulled from the nose gear, confirming that 3,000 psi of hydraulic steering is back where it belongs. A pickup truck engine, a pin designed to brake, and a machine that borrows the airplane's own weight to push it. What's something on an airplane you've always noticed but never understood? Drop it in the comments.